We're going to talk about graphs now. What you see here is an example of a graph. This is called a directed graph. There are many types of graphs. For example, cyclic graphs, acyclic graphs, directed graph, undirected graphs, and many more. We will see them and then we will choose which one is better for our development as we go. For example, here you see the direction of the arrows. They can only travel in one direction. That means it's a directed graph. If we will have an arrow like this, for example, that will make it a cycle because from A you can travel to B, B to D, and from D you can go back to A, which will create a cycle. For now, we're gonna stick simple and just take a look at a directed graph. We're not only gonna use this, as I told you before, in the context that Houdini is a bunch of nodes conforming a graph, but we will transform all the data we can possibly transform into a graph itself, for example, a character rig, or any sorts of hierarchy. If you think about USD structures, they will be graphs as well. So if I keep it with this example, the two algorithms we're going to use to traverse and graph the data of a graph is going to be depth first search and breadth first search. Depth first search, or DFS, will work in kind of like this vertical direction if we're thinking on a tree, for example. If you're thinking on a graph like this one, so the way depth first search work, if we select a starting point like A over here, it's called depth because it will travel as far as possible in one direction as deep as possible. Again, if we're starting at A and we're taking the route of traveling to B next, you will have to go as far as possible until you find a leaf node. You know it's a leaf node because the pointer will be null, same as a linked list. If you think it this way, a linked list is also a graph. In this case, for example, if we're printing each value of the nodes, it will go to A, and then maybe it's going to choose the direction and go to B, and then to D. Next, since we already visited A, it's going to select the next route. So it will go to C, and it has to travel as far as possible. So then it goes to E, but then maybe it goes to F. And then it's going to stop here because this is a leaf node. And the remainder one, since we already traveled this, will be the furthest direction it can go, which will be G. Breadth first search is different. If you think of this way, depth first search is going to go into like a vertical way, while breadth first search will go in this horizontal way. It will make more sense once we deal with trees. But for now, think of it this way. Breadth first search will view the neighbors first. So if we're starting at A, the immediate neighbors of A will be B and C. So we're adding that into our queue. And then if you take B, the only neighbor will be D, and then you don't have any other neighbors. So we already visited all these nodes. So we're going back to C. The immediate neighbor will be E, and then the neighbors of E will be F and G. So if you see that pattern, instead of going in one direction as far as possible, it's kind of going in this radial approach of grabbing the neighbors and then the neighbors of the next ones. So why you want to use one versus the other? When you want to use depth first search or breadth first search? They are really useful depending on the needs you need to prioritize in your traversal. So let's take a look at one example here. I have this grid. It can be a really complex character system, like a rigging with feathers and a bunch of stuff. So lots of connection that almost looks like a grid. And then if we say this is the starting node, there are lots of connections and you're trying to fetch and you're trying to graph one specific node in your chain. If you're using depth first search or DFS, maybe you start at this node and then you go in this direction. So you will visit this node next and this one, and maybe this chain is really, really, really long, have lots of nodes in there. So you visited the whole chain and the node you were trying to find was never there, and turns out it was, for example, this one here. Now you can see using depth first search in something like this, it wouldn't be efficient, while using breadth first search, you will start growing like this. Because if you think it that way, the neighbors of this node will be this one and this one. And then the neighbors of this node can be this one on this one, and then you immediately found the one you were looking for. Or if the algorithm goes to this one next, the neighbor will be still this one and this one. but you find the node really fast instead of going as far as possible in one direction. So that's why you need to select which one you want to use. It will make more sense again in a tree structure. Depth first search will travel in the height of the tree, while breadth first search will travel in width. So how come depth first search travels in one direction and breadth first search behaves differently? It all narrows down to the underlying data structure each uses. Depth first search uses a stack, while breadth first search uses a queue. The difference between these is the structure on how you're adding and fetching your data. Stack will use a LIFO architecture, meaning the last one you put in the container will be the first one to go out. While in queue, the first one you added in the container will be the first one to go out. If you think it this way, stack, for example, can be a stack of plates on a table. If you're trying to grab a plate, you will probably take the last one you added into the pile. You can't just grab one from the middle or something like that. So the last one you put in is the first one you're gonna fetch. In a queue is, for example, in a printer, when you send in a bunch of documents to print. The first one you printed is the first one that's gonna be printed, while the other documents are waiting for this one to be done, and then it's gonna jump into the next one. That's the main difference. So let's start doing the traversal of the graph using this data structure so you understand better depth first search and breadth first search. So let's start with DFS. If you're visiting this node, we will have a condition, for example, while the data structure, while the stack is not empty. We're gonna start at A. This is our root node, and we're gonna add A into the stack. Stacks are usually laid out vertically, like the plates. So we're adding A into the stack. And then the condition is while this one is not empty. In the first instance, we're gonna pop whatever is in the stack. When we're doing pop, we're gonna retrieve this item. It will be by default the last element in the container, in the array, or in the stack. So you will fetch this one. And then you will add the neighbors into the stack. So the neighbors of A will be B and C. So for example, we're adding B and C. We already popped this one out and we have it here. The next iteration, okay, which one is at the top of the stack? It will be C. So we're gonna add the neighbors. We're gonna pop this one, we're gonna pop C, and we can place it here. And we're gonna add the neighbors of C, which will be E. Again, we're going back to the stack. Which one are the neighbors of E? Will be F and G. So we're gonna pop E, put it in here, and add into the stack F and G. If you keep doing this traversal, we're gonna pop this one, add it into this data structure. For example, we're printing this, maybe. So if you think it this way, just by doing that, take a look at what's happening here. If we're starting at A and we go in one direction, the next one is gonna be C, which is this one here, and then E, and lastly G. So we officially travel in one direction as far as possible. That's why it works like that, is because it's using a stack. If you're using a queue, it's gonna be different for breadth first search. So we have our queue. We're gonna add the first element. Let me remove these arrows first. Let's do a queue here. Let's add A into the queue, and we're gonna add the neighbors. So let's do B and C. And then we need to pop. Remember, it's different from the stack. We actually pop in the first one we place it in. So we pop in A, and maybe we're placing it down here. And we keep doing the same. So for D, we will pop. We already popped this. We're gonna travel to the neighbors of B because it's the next one in the queue. And it will be D. We're gonna add that. And we're gonna pop this and retrieve that one. So if you keep doing that, you will see that pattern where we are efficiently and effectively traveling in this direction, fetching the neighbors, as we keep popping the first element in the queue. We're gonna implement this graph and the traversal next. So the same graph we saw before, let's transpose that into code. For that, I'm just creating a variable. It's going to be a hash table or a dictionary in Python. But the correct term for this will be an adjacency list. That's why it's called, even when it's a dictionary, if we're referring this as a graph, it will be an adjacency list. Let's start drawing the graph. Our root node will be A. That's the key, and the value will be a list of the neighbors. So it will be B and C. Next, if we take, let's stick in this direction first. So A, B, and D. The next one will be the string B. And the neighbor, we have just one neighbor, which is D. D doesn't have any neighbors, but we still need to add that into the graph. So it will be an empty list of neighbors. Let's move to the next one, C. The neighbors of C will be E. The neighbors of E will be F and G. Again, F doesn't have any neighbors, but we still need to add it into our data structure, and the same for G. So that's how we move and transpose our graph from a contextual point of view, just a graph, to an adjacency list. Now that we have that, we can traverse it. I didn't speak about this before, we're gonna cover it more in trees, but depth first search, you can do it in 3 ways. You can implement that in 3 ways. It's called pre-order, in-order, and post-order. For now, we're not gonna worry about that. We're just gonna take a look at the 2 ways of implementing depth first search in terms of the structure of the algorithm. One is gonna be with iterations, and the other one is gonna be with recursion. Recursion is key. Recursion, we're gonna use that one a lot in trees and as we traverse to our actual pipeline development. For now, let's define a function called DFS, iterative. We're gonna use iterations. And we're gonna pass in the graph we're trying to traverse and a root. The root is the starting node. So if we're starting at A will be the root. What you're gonna do is establish a data structure called stack. It's gonna be a list. The list is not empty. It will contain the root node. And our condition, as I explained, is while this is not empty. So while we can do the length of the stack. You can just do while stack, but it's not very descriptive. So if you can do while the length of the stack is greater than 0, we're gonna do the logic in here. So what we need is to establish which one is our current node. Our current node will be whatever is on stack. And remember, we are fetching the top of the stack. So our current, you can call it current node, is equal to stack.pop. By default, pop in Python will fetch the last element in the container. In this case, at the beginning, it's just one A. So at this time, current node is going to be A. After we pop, we can just print that. We can print the current node. And then we're going to traverse through the neighbors. So the neighbors of A will be B and C. For that, we'll do a loop. We can say for node in graph of the current node, because it's a dictionary, we're fetching the key. Node. We're going to append the node to the stack. So as we're popping the element at the top, we're going to append the neighbors as we travel, the same way I explained in the graph. This will be by iterations. So let's call in the function, and we're going to pass in the graph and the starting root node, which will be A. And that way we are traversing through the tree. So about recursion, what we're going to change here is, let's create another function, DFS recursive. We're still going to pass in the graph and the root. That doesn't change. And the way we're going to do that is, let's fetch the information of the node. In this case, we're starting with root. And then we're going to loop for node in graph of root, which will be the node we're currently iterating through. If you think about that, root here will become our current every time. And then we do a recursive call. So DFS recursive, we're going to call the same function we are in. We're going to pass in the graph and each node. So it will be each neighbor. And that's it. It's like 2-3 lines of code maximum. But keep in mind, iterative will always be more performant and overall better than recursion. Recursion, the function itself, has an address in memory. And the fact that you're calling for every single node, you're storing that in memory. So not just for time, space is also more consuming. So sometimes it's not a good idea to add just recursion. Whenever you can, always try to prioritize iterative than recursive. But in trees, you're going to be using recursive all the time. Now, if we call that function, then we pass in the graph and the starting node as well. Let's delete this one here. You might see they look different, even when they're supposed to be the same. But we don't care about the order that is printing. All we care is the direction of travel. That's the main thing about this algorithm. So if we take a look at this ABD, it turns out in the first instance it went from A to this one and then to this one. And then it went to the remainder, so C, E, F, and then G. Well, the first time we printed A, C, E, so it went this direction all the way to F. They are the same directions, so we don't care about this order of printing. We always care just by the direction they're traveling. So what about breadth first search? The only thing is going to change, I'm going to copy this function definition, paste it here. You can't do breadth first search with recursion. You can only do it with iterations. So let's just change the name. And this is BFS for breadth first search. All we have to change here, remember which data structure each algorithm is using. This one is using a stack, and this one's using a queue. In Python, all we have to do to make it behave as a queue is to pop the first element every time. Instead of popping the default last element as you do in a stack, we're gonna pop the first one as you do in a queue. So Python, that's why it's so dynamic. Even when you have one data structure, just a list, in Python you can tell Python act as a stack or act as a queue. In other programming languages, you need to specify if the data structure is a stack or a queue. Just by doing that, you should change this name to queue instead of stack, but just to show you, I'm gonna keep it like that. And let's call that function here, BFS. I'm gonna pass in the graph and the root node as well. So now if I run that, obviously the name is wrong, it's breadth first search. But now let's take a look at the direction of travel or how it's actually traveling in the graph. So A, B, C, that will be A and the neighbors. So it's going into this pattern here, and then it's going into D, so the neighbor of B. And then it will go to the next pattern down here, E, F, G. Let's talk about trees. For now, we're gonna stick with the binary tree. What you see here on the screen is an example of a binary tree. The conditions of a binary tree is, for each node, you will have a maximum of 2 nodes as children. If you see, for example, node A, which will be the root of the tree, the children will be just 2 as a maximum. It can be 1, or it can be no children at all, which will be a null pointer. The same way we have a pointer to next in a linked list, in a binary tree we will have pointers to left and right, which will be the children of the node, the next pointer of the root node or the parent node. We're going to stick with a binary tree, and also we will implement a binary search tree. A binary search tree is still going to be similar conditions, having 2 as maximum, but it will work with numeric data. So for example, if the root of the tree is, for example, a number 3 as the starting node, the conditions are that the left children has to be less than the value of the node itself, so it can be 1, for example. But the right children has to be bigger than the node itself. So it can be 6, for example. And the same conditions will apply as you grow your tree. Now this is the parent node for the next children. So the left one can be, for example, 3. And the right one will have to be bigger, like 8. This is valid as well. Can be the same number. As long as we match those conditions, the binary search tree will be properly implemented. We're going to implement this tree here. And let's jump into our editor. There we go. So how can we create this tree? Similar as the linked list, we're going to define a node class. We can create a constructor. And we need to pass in a value. So self.value is equals to whatever value we're passing in. Self.left is equal to a null pointer by default. And self.right will be equal to none as well. Then we can create a function called create node. This will actually create the nodes. We're going to pass in a new value. And we're going to return a node instance, an object with that new value. Really, really simple. Once we have those two, we can create a function to actually draw the tree, or we can call it main, or something that's characteristic of properly implementing the structure itself. Let's call it create tree. Keep it like this. I'm not gonna pass in any value. We can have here a variable called tree, so it can be descriptive. We're gonna use the create node function, and we can start with the first value. So the root node will be A. We can call this root if we want. So the tree has A as the root node, and let's do this in order. Let's stick to the left side first. What we need to do now is to create those pointers as well as creating the nodes. So if we say tree.left, we're effectively going to create this node here, B. And we'll do that by calling the same function, create node, and let's place it. Obviously, this has to be a string. We're dealing with string values here, so that will be B. And now how can we create this one here? We're gonna do tree.left. We are following that chain. So if B was the left of A, and now the left of B is gonna be D. So that's why is the beginning, the root node, which is tree.left. We call in that function, and we pass in the value. Now we can do the right hand side, which will be tree.right, and create node. Put the value C, tree.right, left, create node, E. Again, I'm going tree.right, left, so that's E. And now let's do F, which will be tree.right, create node again, F. Let's go for G down here, which will be tree.right, left equals to create node G. And the last one will be tree.right, right. So it's tree.right, which will be H. That's how we can create the node. So if we call that function here, create tree, now we have the tree. And then let's implement something to print the tree. So for this function, we're going to use depth first search. And we will check about pre-order, in order, and post order in the next section. But for now, let's just call this print tree. We're going to pass in a reference to root. And we can say the base case first. If root is none, then maybe we can return. We're going to print the value, so root that value. And then we're going to pass in, we're going to do a recursion call of root that left. And then root that right. That should be all. We can assign a variable to this even when we're not returning something. We can always put that return value here, return 3, and let's call this a just as a temporary variable. We can set it here. Since we have the reference for that, we can now call the function. So let's call that print3, and we can pass in a. If we execute that, now we are printing our tree. So to finish up this chapter, so we can finally jump into Houdini, we're going to implement a binary tree in a different way, in a more production-oriented code. We're going to start by creating a file. In the same way we implemented before and the same way we did it with the linked list, we're going to define a class for the node itself. We need a constructor, and we're going to pass in a key, which is the value. Let's start with the left pointer, so we keep organized, equals to none is a null pointer. Save that right, equals to none, and the value is equal to the key. You will see the term key often in binary trees or trees in general. So this is for the node. We will implement now the class to create the tree. And in production, you will see a structure like this. Let's call it binary tree. Sorry, that's a class. We need a constructor as well. So initially, the root is going to be equal to none. So we're going to start by defining a findNode method. I call it findNode. We need to attach it to the class by specifying self. We're going to pass in the node we're trying to find and the value. Let's keep it consistent as key. So the condition will be if node is none, or if the value, so node that value is equal to the key, then we're going to return that node. If that's not the case, elif the key is less than the value, node that value. In that case, we're going to return a recursive call of this function, so self.find node, where we're going to pass in the left side and the key. Lastly, if that condition is not true, meaning if it's bigger, we're going to pass in a recursive call to self.find node, where we're going to pass in the right side. Keep in mind in this structure, it's going to be really familiar as we deal with more binary trees. It's always the case in a recursive function to find the base case first. This case, the algorithm is going to keep searching until this condition is true. So if once it reaches this condition, it's going to stop. If that's not the case, we're going to pass in the left side and then the right side. We will use this structure a lot in different methods and different functions to deal with binary trees. So the condition here of one side being smaller than the other side is a characteristic of a binary search tree, not just a binary tree. Binary tree can have any value with a maximum of 2 children. in this case, we're implementing for the case of a binary search tree, because it will take too long to split just for binary trees and binary search trees, and there's no time, especially in this workshop, so we're gonna keep it as one, but it's just for you to keep in mind. Let's jump into the next method. We're gonna insert a node. Let's call it insert self and the new key. The condition will be if self that root is none, then self that root will be a new node with the key we're passing. So node of key. Else, we're gonna create a helper function called insert recursively. Gonna pass in root and a new value. We will implement this helper function next. Now the helper function insert recursively, attach it to the class, pass in the node and the key. The conditions here will be if the key is less than the value, and then we do another check if node that left is none, then we can insert node that left is equals to a new node with the key. Else self, we're gonna do a recursive call. You guessed it, we're gonna pass in node that left and the key. Then our else condition outside this first loop is for the right side. So if node that right is none, then node that right will become a new node. I'll pass in the key, else self a recursion call, and we'll pass in the right side and the key. Again, familiar structure. Doing the base cases and then passing the left side and then the right side. So these are kind of like the most standard methods to have, but we can also implement some really nice functionality as well. We're gonna call this one insert at node. Really useful, for example, if you have a character rig with really complex structure and you need to insert a bone in between two bones and stuff like that, or a new prop at the hand or as a new clothing prop or stuff like that. So the way we're gonna do this is we're gonna set the parent key, I mean the node we want to insert at by value, the key itself of the new node, and we can choose if we insert to the left of the parent node or to the right. It will be unwise to have it here like left and right, because we can narrow it down to a boolean. So we can say to left. So if this is a boolean, it will match that context. So if it's true, it goes to the left. If it's not, it will go to the right. So you don't need to have insert to the left or insert to the right. Basically, if this to left is not true, it will be the right side. So it's more like an elegant and smarter way of implementing these kind of things. So the parent node will be equal to self that find node. We're calling in that method self that root and the parent key. This will return a node. Now we can check if the parent node is not none. Then we can do another check. If the condition is true to be to the left side, so if to left, then we do another condition. If parent that node that left is none, meaning we can actually have space there to allocate this. We will do parent node, sorry. That left is going to be equal to a new instance where we're going to pass in the key. We have officially inserted a node there. But if we have something in there already, we can just print, for example, left child already exists. Then at this level, we can do another comparison. Else, if basically, if this is not to the left, will be to the right side. In that case, we will do parent node, and this is parent node, that right is none. It's going to be similar. Then the parent node, that right, will be a new instance of the node with the new key we're passing. Else, this will mean it already exists, so we can do right child already exists. And then if none of this is true, we never found that parent node, we can print parent node not found. Oh, this is node, not none. This is just my editor complaining, but it's not an error. So this is how we implement insert at a given parent node. And you can keep adding more utilities and more functionality to this class. The last one we will implement here is the actual traversing of the tree. I didn't mention this before. We're going to use depth-first search. In depth-first search, you have three ways of implementing the algorithm: pre-order, in order, and post-order. So let's do in order. And there's a reason you want to use one or the other. Call it in order traversal. I'm going to attach it to the class, and we're going to pass in the node. So we'll do if node self that in order. It's going to be a recursive call. We're going to pass in node that left. You get the structure by now. You're going to print the value. We can specify this to have a nice printing like that. And then we're going to call in the right side. In order traversal of node that right. This is the structure of an in-order traversal. Basically what this means, if we start with pre-order traversal, it will be, the only difference is this. We will fetch the information of the node first. In this case, it's just printing node at value. You can grab other attributes or do something else, but we will grab the data of the node. And then we will pass the left side and then the right side of the tree. That will be pre-order. In order, you pass the left side first, and then you query the value of the node, and then you pass the right side. In post order, it will be like this. You pass the left side of the tree, the right side, and then you query the value. The reason why you want sometimes one or the other, it will depend on which node you're trying to prioritize, for example. If we're doing pre-order, like this will have the root at the beginning. Once we fetch the structure of the tree, we will have the root first, and then all the elements of the left side of the tree, and then all the elements of the right side of the tree. If we're doing like this, which is in order, the root will be at the middle. So we will fetch all the elements of the left side of the tree first, and then we have root, and then we have all the element side of the right tree. And it's going to be obviously for the post order, we will grab all the elements of the tree, and then at the end we will have root. So for example, in this case of having it in order, let's keep the example of the character rig. Let's say it's not symmetrical, which in production, it will probably almost never be completely symmetrical. And then on the right side of the character, you have like a really complex weapon system attached to different kind of clothes and different kind of things. And it's really complex. If you're doing it this way, you're fetching the left side first. So maybe you want to prioritize finding a node in the left side, which is not really that complex and is different from the right-hand side. In that way, for example, you can use in-order traversal and different kind of things. If you're doing, for example, post order, this is basically like reversing the tree. Remember, we have the node root at the beginning and then we branch out to the left and to the right side. Doing it this way, you will prioritize the leaf children. For example, maybe you're trying to fetch the last leaf node in your rig, in the character rig, because you're trying to find something in the hands or stuff like that. So as you can see, it depends on your needs. For now, just to print the tree and to create the actual tree, we're gonna keep it like this, which will be in order traversal. Let's finally create the tree. We will do that in the old-fashioned main function. So we will do if name equals main. We can start creating the tree here. Let's call it BT for binary tree. I'm gonna call in that class. And we're gonna insert some nodes with the usual insert. Give it the value 3. We insert another one, give it the value 2, and another one with the value 4. And then let's test our insert at node. I'm gonna pass in insert at node 2, insert the children 1, and to the left. True. And then we do insert at node to test it further. In the node with value 4, we're gonna insert 5. Obviously 5 is greater, so that will be to the right. So we're gonna say false to this Boolean. And we can test our traversal or printing, which is gonna pass in the root. If we execute our code, then you see our tree. At the beginning, we inserted 3, 2, and 4, and now we have the full tree because we inserted at the left-hand side of 2, 1, and to the right-hand side of 4, 5. So now we have the order 1, 2, 3, 4, 5. And to recap, let's just cat this, or let's just actually check the code. We are passing 3 as root first. This is the order we are fetching it. And then we are to the left and to the right. And in our printing, you can see the root is at the middle because we're using in order traversal. So the main take of all of this is for you to start thinking in a production way. This is how you're gonna see code in production by setting it into classes. Different from the version we did with the linked list. These are not loose functions somewhere in the code. They belong to a class and is properly structured. Ideally, this will be in your main hub, in your pipeline. So if you need to create trees or use some methods from one of these utilities, from one of these classes, you can call in that function, this Python script from your library and start applying that into your graphs or your trees. The last thing I want to show you here, you will see all these methods inside the class as members of this class. Sometimes in your code, you do need a function so you can call it quickly without instantiating a class. For stuff like that, let's put it at the end. You can use it basically in 2 ways. It will be with this decorator. If you use a class method and then you do a function here, let's call it just test. I'm not gonna use this one. But now, if you specify CLS and then some value, you can return that value or do something with a function. So this is a function this function lives inside the class, is a member of the class binary tree in this case. But you don't have to create a whole instance of the class itself to be able to execute this. And the way you will execute this is, for example, in your main function, it will be with the name of the class and then the name of that method. So you can pass the value 5, for example. If you run this, it will return the value 5. As you can see, I'm using the class with a new method, but it's not defined as self. So this is a class method. Really useful, but sometimes you need something even that's not attached to the actual type of the class itself. So what I mean by that is something called a static method. So if we use another decorator and we use a static method like this, you can define a function that it doesn't even require to have a class input. So we will do a method called compare trees. If you see this, it looks like a loose function, but is indeed attached to the class. But again, you don't have to instantiate and create an object, like a whole instance of the class itself, to be able to execute this method. In this case, we will pass in tree A and tree B, for example, and we will do something in here. And I'll show you that next. So let's quickly talk about the logic of comparing trees. If we have two trees as an input, tree A and tree B, for example, this is A and this is B, the way we want to compare it is not only by value, but also in shape. If we do in depth first search, we're going to retain the shape of the trees and the values. If we're doing breadth first search, we will be traversing in this sense. We can only grasp the values. So we will do depth first search and we will compare that. We're going to end, so our base case is once we reach the leaf nodes, meaning when you have null or none as your next pointer. So let's implement the logic for that. What we're going to say here is we're going to pass tree A and tree B. And we will say if A is equals to a null pointer or none, and B is equals to none as well, that means we reach the end of the trees, and this will be our base case, and we're going to return true. Then we will check if A is none or B is none. This is false, because if in the first case, if both matches the criteria and strictly is the same, it's going to be true. In this case will be if either one or the other is not the same, is not a leaf node, this will return false. So we're checking structure here with these first two conditions. The next one will be by value. So we'll say if A, that value, is not equals to B, that value, we're gonna return false as well. And then the recursive call of this will be to return compare trees. We're gonna pass in the left side first, left side of tree A and left side of tree B. So A that left and B that left. And we're gonna pass in compare trees and the right side. So A that right and B that right. That's how we compare values, and that's how we compare by shape as well. So there's more complexity when you're dealing with recursive calls in a class. You need a reference to the class, so I had to add in here the prefix, the name of the class, and then do the recursion call at the end. So what I did in main is I created my tree and then I just copy pasted and changed the name of the variable so it's another tree. And then I'm calling in my function here and passing in the first tree that root and then the second tree that root. That way we can traverse through both trees. Now, as humans, you can see they are indeed the same tree, and the fact that I just copy pasted is going to tell us it's the same tree. But for a machine and for the system itself, that's why we need to implement a function. So let's test it out. We're going to call in the function and it's printing true because the trees are the same. So let's try to change something in the tree to make sure it's indeed working. If I change the value here, for example, now 3b is going to be different. So if I run that, now it's false. So we know it's working. So the case for this will be, for example, you don't necessarily need to create these trees from scratch. That's why we're creating class methods or static methods. And it will be your job in a, for example, in a case, let's say user A is sending you a character rig, and then user B is sending you another character rig. And it's your job to create a tool to compare both rigs. That's how you do, and that's why you do some structures like this in production. Hello everyone, welcome back. We're finally here. Let's talk about Houdini. The first thing we want to check is go into the help menu, click about Houdini, and show details. There's a lot of useful information here, not just for your system, but what's happening in your OS and your configuration files. The most important part we care about at this moment is in the environment section. Later you will see why it's really useful, and I'm sure you handled environment variables before. Just as a quick overview, in production, when you're kicking off a production in the project management side of things, this is not necessarily your role, but what's happening behind the scenes is once we establish all the biddings and we have approval from the client to start something, we will have internal kickoff meetings with different departments. One side we will go into the more creative side of things, and the other side we go into the technical side of things. So into the technical side of things, all the required departments will be there present in those meetings. And we want to establish requirements for the production. If it's a game or a VFX movie or advertising and stuff like that. For example, it's a show that relies really heavily on massive simulations and you're experimenting with new GPU solvers and stuff like that. That kind of information will be allocated in documents and into the servers. So when you have the crew established and each artist of each person in the crew working in the actual production, once you log in into the show, lots of environment variables will be triggered. Usually communicating with a bunch of YAML files, XML files, CSV, and a bunch of configurations depending on the studio, but lots of things will be set for you. That's why you have access to a lot of tools, probably coming from old shows or new versions of the tools and stuff like that. We're going to work in our mini version for our home pipeline a little bit later, but just for you to be aware, there's a lot of things happening. So as you're setting your local configuration in your Houdini files, you will probably be working in the Houdini config folder. That's very local, that's just for you. So we need to start thinking more in production where these tools, where the code you're deploying will be later stored. We can see information here about the environment variable set for different versions, tooling, Python paths, and whatnot. So really useful to have a grasp on this window. So if we start talking about Houdini itself, let's do a quick recap in all the places you can write Python code in Houdini. The main window will be the Python shell. I will recommend to have one open regardless of your layout. You always need one. This is where you're basically gonna print everything. This is your logging window. This will make sure everything that's supposed to be working will work as intended. You can also do programming here. If I do, for example, print hello, it's gonna print hello. It's a basic Python console. But it's also really important when you need to test small things, but they are really useful. For example, sys.path. Really important one. We will be using this one a little bit later. But small short scripts like that and your basic log information will be here present all the time. So please have this one open. The second place is the shelves. You see lots of these icons in different shelves, pretty much based on department or different needs for your work. If you create a new one, I just created an empty here. Every default tool in Houdini is already Python based. So if you right click and go edit tool and see the script, you will see it's calling other libraries. Sometimes it's just a definition in the script itself. But I mainly use this one as a testing stage, not as my main development tools. But it depends on your studio, it depends on your workflow. For me, this is a testing area for some quick tools or prototypes I'm developing. Keep in mind, by default, your shelf will be stored, the actual shelf will be stored in the config folder. So if you lose that folder, your shelf is gone forever. In production, you can store in the main hub a shelf file, which can be triggered by the environment variable configuration of the product. That way, once you open Houdini, you have a established set of tools for your show, which is very similar to the way you work in Maya. So we can use it that way too. The other place is in the networks. Really useful Python sub. Primarily, this will be used with geometry. Not just with geometry. You can also read files, call libraries, all the other stuff you can do with the global API itself. You can have parameters in the node and read and interact with those parameters and a bunch of things. But it's mainly used based on the input coming from the geometry. So we can use it to set attributes, really, really useful. The other way will be once we create an HDA. I always start an HDA with a subnet. In a subnet, you can tweak the parameters. And you can edit and add a bunch of different data types. If you add a string, by default it's going to be a really short field. If I hit apply, it's a tiny, tiny label. But you can actually make it switch to a multi-line string. And you can choose the language, which is really cool. Now in here you can start typing Python code. There's a different way of executing this, which we will see later. The reason I start like this is when I'm prototyping an HDA. Later, this code will be embedded in the HDA itself, so we will see that. The other place is going to be stage. If I drop anything in there, another pig head, for example. USD is all about hierarchies, and this is a graph. So we're going to learn how to traverse this, grab data, metadata from your stage. And the final place we'll see is in tops. Lots of cool Python tools in here as well, like partitioner processors and stuff like that. Those are the main places we're gonna be scripting Python, and we will create external libraries and call them, deploy them, and implement a home pipeline. Let's start doing some exercises. Another refresh on the Python API. Let's do an exercise where we create a network like this one. So I'm gonna delete this one, and let's create one programmatically. So our aim is to do this. Create a geometry container. We're gonna add a null. We're gonna add a file node. We're gonna set all the parameters and maybe add more nodes in a chain. So we can parameterize all of that and create some tool with this. We're gonna do it in the shelf. Again, this is my testing stage. So if you go right click, select new tool. You don't have to import Who because we are inside Houdini, but once we launch Houdini and start doing some commands from the terminal, it will be required. So it's a good practice to import Who anyways. So how are we gonna work? We're gonna work in context. This context is the object context and is the place we're gonna place our initial node. So let's call this one base node. It's gonna be Who.node. Where we're gonna place that node is in this context, obj. Now we can access the create node method. It's gonna be of type geometry. I think it's just called geo. If you middle click, you will see the name of the node. So that's the node we want. And we can give it a name as well. The second argument will be the name. So let's call this root node. Then I hit apply, and now you have the new tool. In the options tab, you can give it a name. Let's just call it test. And you can give it an icon. Houdini comes with thousands of icons. So I randomly select one. There we go. Now if we click this, we have a geometry node in object context called root node. So we know it's working. I'm gonna keep deleting this every time. It's usually a best practice to add the condition if the node exists, create a new one, and things like that. But for now, we're just gonna keep deleting it as we go. Now that we have the base node, one of these, it's gonna be different if you wanna create a node connection here. We actually wanna go inside. So we need to fetch that path. Let's create a variable called root path. And we can fetch it by calling in that path method in the base node. And we can print that. So if I hit apply, this is the path we want. So we have access to the path we were trying to create a node. So let me delete those. We know it's a path. So now let's start creating those nodes inside the base node. Let's call this one root null. It's going to be a type who that node again. The path is the root path because now we have reference to that path. And then we can call in the method create node. It's going to be of type null, and we can give it a name like root. Now we're going to create a node connected to this null node, which will be a file node. So let's give it a variable so we can reference it. File node equals to root null that create output node. Let's give it a type. I think they're called file. You can always, if you don't know the name of the nodes, because there are so many, you can always create one manually. Middle click and check the name of the node. Not the name of the operator, the name of the actual node class. That's file. If you don't give it a name, it's going to come by default, like for example this one, file1. Let's delete those. And then let's connect a final null to that file node. So file node that create is the same output node, and I'm gonna give it the type null, and let's give it a name tail. Hit apply. Have some errors, have a typo there. So it's create output node with capital N. We go here. Now we have the structure we want. Root, the node, and tail. So let's modify some parameters from the file node. This is a really good one because it has all the elements we can play around with. It has these drop-down menus. We have string fields, we have buttons, we have sliders, toggles. So it's really good. So in between this, let's modify some of these by default. So in this node, how can we access the parameters? This is basically a dictionary. If you think about the name of the parameter and the value is going to be a key value pair. Later we will see about the quarks node and how to deal with that, but for now, we're just going to map it. So if you hover your mouse, you will see the name of the parameter this time, not the name of the node. It's called, for example, file mode. And this is a drop-down menu. It's going to be index-based. So the first one is going to be 0. As you can see, the default will be 1 because it's read files. So let's change this to 0. How can we access the parameter? We have access to the node, therefore we can say file node.parm, and the name of this is file mode. We can call in the set function and set the number 0. So we copy this line and let's change another one. We can add a string here. Think in pipeline, if you're reading a bunch of strings, you're reading a bunch of files from a CSV document, for example. You can loop through those fields, through those entries, and set this string parameter. So this one is called file. And we can set a string, some path. Let's modify another one. We can press buttons as well. This parameter is called reload. We're not going to press it because it's going to error once we load the network. But if you have a reference to the button, this is called reload, for example. You can call in the method press button. That way Python will press the button in this and it will reload the geometry. I'm not going to use that one. Let's change some of these. No, this is the same as dropdown. We already saw that. This is useful, a toggle. The parameter is called delay load. So delay load is a toggle, 0 or 1. By default is off, so we can change it to 1, and we can move these sliders as well. Hover your mouse, the name is cache size, and we can set values for that slider. Default is 0, let's set it to 5 or something. Hit apply, let's delete this network, and call in the whole hierarchy. So root node, the names. Now if I click this, you will see, obviously it's failing because we don't have this path, but I switch this one from the default of read files to automatic, and basically all the settings I'm giving it to the file. If you follow this logic, you can create really big networks with default parameters and automate lots of things. For example, you need to retopologize or you need to do polyreduce in like 1,000 different assets. With this, you can call them, drop a loop, set all the parameters, and send that from the command line. That way you have your assets ready to go with one click. We're gonna keep going with graph traversals. I have a scene here with a bunch of nodes and connections. It will be an example you're doing this kind of motion graphics scene. And maybe you have the feedback to change the noise pattern or do something else. Try to find something in the network. Now, in a production sense, you can be doing your own script using different company tools, which will be lots of nested networks and stuff like that. You could be reading someone else's file, and it can be many, many different scenarios where you need to find some specific node and tweak some values. I'm gonna pretend this is like a massive network, and then you have maybe sub networks and they grow really, really big, which will be the case in production. I'll tell you a story a little bit later. We're gonna do a graph traversal with the algorithms we saw. We're gonna use breadth first search to try to find something that will change the noise pattern, like the frequency or just altering the noise based on the directions we have. It's a very common thing to do in a production. If you're dealing with massive networks, can be like dead ends at some point and things like that. So how can we efficiently find a node in there? Let's think for a second without even looking like one by one all the nodes and connections, which some people do that. There has to be something in here. Can be like a node or can be like a vex script or something else. But potentially we have some common things like noise amplitude, noise offset in some nodes. Can be, again, can be a program doing that. Ideally, in a well-organized production, you will have proper names. That's why it's important to have proper labels for everything. But sometimes it's not the case. But we're gonna think and we're gonna do that as our starting point, where we're assuming there is some label, some parameter in the network that will drive how the noise is conformed, how the noise is structured. So how can we start this? We're gonna do a graph traversal, and the root of our graph will be these guys here. We can visually see they are the starting points in the network. So we're gonna iterate through each one of those and all the connections, the neighbors, the outputs, and we will deal with this kind of scenario. We're going to a shelf, start a new tool. You can give it a name. For now, let's just do BFS for breadth first search. And start doing our program here. At this point, we forget about the viewport. We don't care about that anymore. Just gonna stick with the Python shell. So how can we get the nodes? Let's start by importing who, as usual. Again, you don't have to do that. So the root nodes, let's create a variable called root nodes, is equal to, Houdini will have a function to add all the selected nodes in a list, which is called who.selected node. You can see here in the dropdown. This will return an array, a list of the selection. So if I do this, it will be an array of that selection. Now we can iterate through those. So if we do for root, those will be the roots in root nodes. let's just print root to make sure our tool is working and we don't have any issues. So these guys are selected. Let's run this. And you see the root nodes, box, sphere, and the rubber toy. Great. So that's working. You're going to implement a function called BFS for breadth first search. Let's do it here. Breadth first search. And we're going to pass a root. Because for each root node, we will call in that function. It's going to be like this, where we pass in each node in the selection. So in this function, we will establish a data structure. It's going to be a queue because this is breadth first search, which will have the root node. So we're starting with that. You know the condition, while the length of the queue is greater than 0, meaning while the queue is not empty, we're going to have a reference to the current node we are iterating. So current will be equals to queue.pop. Remember how we pop from a queue in Python? That will be pop 0. And we can print the current node, so we can see what we're doing there. And then we can do the loop. So for node, we will do the output connections of each node, and we will do that with iterations. So for node in current.output, this is a Houdini method that will give you the output of the node. So for each node, for example, for box, it will give you the output, subdivide, and so on. So now we're looping through those, and we're going to append that to the queue. So we're going to append each node that we found. For now, it's just printing. So let's make sure that's working. I have the 3 roots selected. Let's execute this. And let's take a look at the printing. Remember, we're doing breadth first search. So I'm expecting to see a pattern like this radial pattern I showed you before, because we're traveling in width first. So if we're starting at box, for example, you can see here box 1, and then we see all the selections. If we follow box 1, the next one will be subdivide 1, which is this one here, and then we will see the neighbors here. So indeed, I can see null 5, and then null 4, and then ray 1, and then it's going to travel to all the neighbors. So it's doing that for all the connections. Let's take a look at the connections in the network. Sphere is going like this. It's doing some poly reduction. We don't care about what's happening in there. We're just trying to find some common things so we can alterate and do our direction for the tool. You have a bunch of networks, and you see the pattern how BFS and depth first search is working. I'm not doing depth first search because, as you know, depth first search will travel as far as possible in every direction. Now, right now, I can tell you this node is the one doing the noise, the mounting node. We as humans can see that, but we're trying to programmatically find which node is doing that. So if you think about that way, how many times are we visiting these networks down here? Or if we have like a super massive long with nested networks and things like that, we don't necessarily want to travel as far as possible on every direction for every root node. Because it could be the case like this. The node we're trying to find is really close to one of those root nodes. It could not be the case, but still is more efficient to use it this way. Since now we can see the pattern being explored by breadth first search. Remember, it's not depth first search, we're using breadth first search, so it's BFS. That's why the tool is called BFS. We can start exploring the conditions for the node. Each node will have a list of parameters, which you can access with the method .params in the node. Let's implement that. Going back to the edit tool, and let's define another function. Let's call it find offset. For now, we're assuming we do have somewhere in there a parameter that's going to control the offset we're trying to find. So we're going to pass in a node, and we're going to loop through each of the parameters of the node. So for parm in node.parms, this will return a list of all the parameters. we can do a condition. So if parm that name, the name of the parameter, is equals to offset, we found not just the parameter, but the node we're trying to find. So let's return true, right? So with this function, how can we insert that in our traversal? It's really handy to have print statements because that's where we know we need to do some action. So after we print this, let's do if, remember this is returning a boolean, so we can use that. If find offset, calling in that function, we're passing in the current node. So if the current node is iterating through has that parameter in there, we can do some other printing so we can keep debugging this. For example, parameter offset found in node. We can give it a format, that format, and we'll pass in current. And we can actually break the loop. That way we don't keep traversing unnecessarily steps if we already find the node we're trying to find. We can also do another function if we add an empty array here, where if this condition is true, we can append to that array all the different instances or all the different nodes that will have the offset parameter in the node. Because it can be a script, can be a node, can be different nodes with the same name offset, or some kind of offset, not just offset. So we can also keep adding that to the program. For now, we're gonna keep it simple, and let's just keep it like that. Remember, we're breaking as soon as we find some node that has the parameter offset in the node. So if I hit apply, we're gonna select our roots. Let's make some space here in the terminal. Let's execute this. And we found some. We found the node, parameter offset found in node mountain1. Let's keep an eye on what's being printed here on the traversal. This is why it's efficient. If we're starting, for example, in this node, box1, up here, indeed we're traversing all the way to the end, to this for each end one. It's the nature of the network. These guys don't have any other neighbors, it's just one straight chain. So I'm expecting to see this for each one here. There we go. And then it's going to the second network. Sphere 1, all the way until it ends. But let's take a look at this. If you see this, from box 1, it goes all the way, it goes until it reaches this final node here, the for each end 1. Now let's take a look at sphere. Keep traveling in this direction. The nature of the graph will also travel from this polyreduce to the same branch until here, but it also travels to RAID 2, it goes here, and so on. So the rubber toy is also traveling to these same networks, to RAID 2 until the end, and its own network at the end to for each end 3. So let's not break it and take a look at the printing again, so you can understand why it's efficient. Let's just comment this one. Let's do lots of space here. I'm gonna select our root node, and let's run that script. Now if you see this, from box 1, subdivide 1, let's take a look at these transforms, for example. It's visiting transform 1 one time, but it will also visit that one with, if we're starting as sphere, at the second root. You see, there it is again. And the same thing will happen with the rubber toy visiting transform 2 and transform 3. So that's transform 3, 2, and so on. The reason we're breaking, have to do space all the time, is because we want to stop as soon as we find the node we're trying to find. So by running this again, to show you one more time, the first time we are indeed visiting from box all the way to the end, But sphere, in theory, should be also going through this network again because it is connected if you follow the chain, and also this one here. But it never goes there. So transform 1 is only being visited once. And if you see that, it's just here. And you never see it again. So if these are massive, massive networks, you never went there. You don't care about going there again and again because you already find the node you're trying to find at some point. So you already save a lot, and I mean a lot, by doing that. And now that we have a reference to the node we're trying to find, we can set that parameter. So let's go back here. At this moment, we're just printing, but we can also set that parameter. So it will be current.parm offset set. Let's just do some random number. Apply. So if we look at our viewport here, do that. You can see now we found out which parameter we're trying to change. And if we're doing it like an HDA or a tool, we can add a slider or something else to control that noise pattern or the direction we want to go. Now you might be thinking, yes, we are visiting the nodes, and the nature of the graph is, if you're doing breadth first search, to potentially visit this twice if they are connected. And there's already Houdini functions, for example, like children of the node. If you select this one, the root node, the main one, and then you do the function that children, it will grab all these nodes in here. And it will create that in an array, in memory. It will store all of these in memory. Indeed, just one for each node. So you're not traversing these networks twice, as we're doing right now. But we are storing all of these, all the children, in memory. And then we will need to traverse one by one. So if you think about this example, by grabbing the children, time and space will be O of n. By doing breadth first search, time is not O of n because we're not visiting every single node. We are doing breadth first search. So time will be, for example, O of m. M is nothing right now, but you can specify if you say m is the width of the tree. So m is equal to whatever is the width of the tree. Worst case scenario, we have lots of horizontal nodes that we need to add into our algorithm. But if you're doing, for example, stuff like this in a technical interview, you need to specify and tell your interviewer m or whatever variable means the width of the tree. You can't say n means the width of the tree because n as a standard means all the nodes, like every single node or element in your scene. N space in our algorithm is constant because we're not storing anything extra. We're not doing a new array with all the children. We're just visiting the nodes. They already have a memory allocation. They have a space in memory, and we're just visiting the node. We're checking some things, and we're going outside and checking the next one. We're not storing anything extra. Once we find our node, we're just setting parameters. So space is constant. So keep in mind that as you're doing your traversal, this can be a really complex character rig. This can be a really complex network system. And in production, I've seen some stuff. It was a case in a company. We have this tool to create some action in some assets. This tool was being developed like in a lapsus of 8 to 10 years. It started as this testing network, and then it jumped around so much, not just in between people, it jumped in between departments and team inside the department. At some point, it landed on my hands. And I'm not kidding, it was like a complete maze. So many networks, so many nodes, so many dead ends. Some things were just experimental. It was like patching this massive Lego set with infinite amount of nodes. And it was almost impossible to figure out what kind of things each network was doing. So using stuff like that, I was able to pretty much narrow it down to the functions and only the nodes I care to develop the tool further. Let's improve this, going into a more production-oriented method. The way I show you here, I did it on purpose so you can see how the algorithms are traveling for each node, for each network. But as you saw before, you need to select these guys, run this, you get everything in there. But indeed, you are visiting probably multiple times nodes, many times the same nodes, depending on the connection. We can improve that. We can add a statement where if we visited a node, we're gonna mark that as a node that we already saw. That way we don't have to traverse twice to the node and we can ignore it. It will be even better and even more efficient than it already is. But I wanted to show you all the traveling and all the printing statements so we get familiar with the architecture. What we're gonna do next is to move to the next level. At the moment, the shell will be a file on disk. And we're talking about your computer, your local machine in your house. You need to start forgetting about that and not thinking in local way of storage. That's not how it works in a production. We're gonna talk about pipeline a little bit. We will go deep into this later, but for now, it will be a quick jump to explain some things. In a production, a game, a advertising shot or TV spot or a movie, there's some common things, and this will depend on the studio and the production itself sometimes. Sometimes in the office, users will have a machine, a physical machine, and a desk, which will have amount of RAM, processor, and whatnot. Lots of times it doesn't work like that. Even if you have a physical machine at your desk, you will never store anything. And by anything, I mean geometry caches or tools or any kind of script or anything you're doing. You will never store that locally, like in a documents folder or in your desktop and things like that. In most studios, you don't even have access and permissions to do things like that. So you need to know how to traverse and get your mindset on different kind of structures and how it works. Usually you will have a server. This will be allocated for your production. If this is a movie or a game or whatever, you have allocations for, I'm gonna call it show, it's gonna be a product at the end. You have allocations for all the resources in terms of GPU power, CPU, RAM, and storage. A chunk of that server, let's say for storage, will be split in for departments and users. In this case, we're pretending these are employees. So employee A, B, and C. Each employee has access to the server. In the backend, there's a lot of configuration. Some employees will have more permissions than others for leads, supervisors, and stuff like that. But ideally, everyone will connect to the server. We're doing an example with we are storing geometry. We're saving some geometry into the disk, into the server. So each employee will have access to the structure of the show or the product itself. And it will be split in based, for example, if you store in geometry, you will have a geometry folder. And if you're using Houdini, it will be a structure driving Houdini to save things in those folders. All of this will be pre-configured in your environment variables. So if you're doing caches or temporary files or processes, you usually have a temporary folder. If you're doing textures, you'll go into the textures folders and so on. You have to make sure you follow the structures for the company. And then if this is all the geometry being saved for that specific game level or for that specific show or sequence, it will split even more. Usually you have folders with the username. And then if user A is saving a geometry file, it will go here and then at the end in the corresponding geometry folder for that user. That's how we can start developing and creating a pipeline. User B can also access these files for user A, and it will have its own folder and files. And every user can access that, and there's gonna be like an intercommunication to be able to grab that. This will be stored at this level in the main geometry section for the DCC, depending on the structure of the company. And obviously all of these will be stored in the main server. This is just, for example, for one department that is just in charge of modeling, doing some texturing and things like that. The same way will be for different departments, a different allocation in the server for different needs, and they can read all these files too. And that's how you need to start thinking in this kind of communication. Even if you have like a physical computer at the office, or you're connecting somehow to the servers of the company, you will never save anything locally. So if you're doing your snippets and things like that, and everything at the moment, as I'm doing right now, is purely in my local machine, it's not going to work like that. You will still have some allocation in the server for some experiments or for some development you're doing, not only strictly tied to these kind of folders. But that extra allocation of space will be something in the server as well, or something very specific in your local machine that will have communication with the server. I'm showing you all of this. We will go into a step of doing our home pipeline a bit later, just to keep you in mind that we are doing things locally at the moment. Me doing this shelf and things like that. But we're gonna take it one step further, not all the way into the main pipeline yet, but we're gonna take it one step further into a production-oriented way of working. First of all my code is here, straight into the tool, into the node. And this is a shelf. In the current show, I'm logging. So if you're doing lots of tools like this, and then you switch to a different show, you're gonna lose all of this because the configuration is gonna be different. And the best way to tackle that issue is to not have the code directly into your tools. Again, you have an allocation in the server. You can store your code there. It's not just for you. Other people will be able to read that code. So sometimes it goes into a location in the server, but the way we're gonna handle later is to do in a repository. So people can update the tools and things like that. So this is great for experiments, but now let's start to do something more production oriented. We're gonna work for now in stage. I have a graph here. We will see some Python USD Solaris things a little bit later. For now, it's just in the context of graph traversal again. I can still use the shelf or any other Python input in Houdini, but for now, I'll just stick with the shelf, but I'm gonna call another library. And this library is still gonna be in my local disk, but is one step further than doing it all here. Just one tool with the code in there. There are some places in Houdini that Houdini will read scripts by default. So if I go to my Explorer here, for example, in Mac is a bit weird. You need to go in this location, basically. It's a hidden file library. And then you go into Preferences, and then Houdini. It's a really, really weird location, but this is where your main Houdini configuration is. In Windows is in Documents, and in Linux I think is in the User folder. It doesn't matter because later we're not gonna use it like this, but just for you to be aware, you probably don't have this folder yet. But you need to create a scripts folder where your Houdini configuration file is. You will see here the environment variables as well, if you need to set that, and a bunch of other things. You see toolbar, this is where your shelf is. You can see the default shelf, and you can create more. Again, it's not the best idea, and you will never do that in production. But for now, this is a good place to start doing some scripting, because we will deploy this a little bit later. So you create a scripts folder. Houdini will understand this, but you need to give it more so we can actually start importing libraries and creating Python code. Inside the scripts folder, you need to create a folder called Python. Once you create that, this is where you can start doing your modules. Obviously, for you, this will be empty. But if you create a folder and give it a name, that's the name of the main module you're gonna be calling, so give it a good name. I'm calling mine USD utils, and you need to give it a constructor right next to the folder. This is an empty Python file, but the name is important. This is how this will become a module, by having the constructor next to it. It's just an empty file called init.py. So it's double underscore init double underscore .py. This is a constructor. Inside here, you will do the same. You can see I have another constructor here. This is where we're gonna create our Python file the main one to do all the logic for our program. So if you're, I'm gonna open a terminal here. Let's go into that location. I can see my constructor. This is where I'm gonna create a new file. Let's call it usd traversal.py. And just for testing, let's just do print hello. And that's it. If you see the structure here, if I go outside, I'm in the main location for the Houdini configuration files, scripts folder, Python folder, and then I have my modules there. Inside my main module, which is called USD utils, in my case, I have another constructor, and now I have the file in there. So we're aiming to call this file from Houdini. Let's do that. Houdini will know about this path. So let's create a new tool here. Let's give it a name, USD utils, because we can have many things in there. Let's give it an icon, why not? I'll just choose some random stuff for now. Okay, that's it, my USD utils. We're starting with the usual import whom. And we need a library, a Python library to reload Python modules. That way we don't have to close Houdini and open it to refresh it every time. We're just gonna keep coding freely and Houdini will update automatically. That library is from import-lib, so you do from import-lib import reload. This method, this function, will allow us to reload any module we're bringing into Houdini. So now, this from is where I'm gonna call it. In my case, if we go back here, is this name, sorry, if we go here, is this name here, USD utils. So you don't get lost. Again, Houdini configuration, files, scripts, Python, and I'm calling the name of the folder. I can call it like that because we have a constructor next to it. And then we can call this module here. So we can say import USD traversal. Now I have that, and now I can reload it. So if I do reload USD traversal, this will be reloaded every time. We can execute this. So let's go back here to Houdini. If I print this, you can see it's printing hello. I don't have that code here on my tool. I'm reading the code I'm doing in my editor here, which is really, really handy. So now you can start doing your tools in a file that can be deployed later. This is not just inside a shelf in Houdini. It's a file on disk that you can share or move it into a proper location. So just keep in mind, everything I'm doing here will be executed in Houdini. So let's talk about the project. It's a better version of the graph traversal. USD is great because it works in hierarchies, and the graph itself for USD is also a parent-child relationship. So the example for this task is USD will have lots of different configurations where you send in and the way you're manipulating the hierarchy of the assets. You see this network here, again, is gonna work for massive, massive networks, especially with USD, because it can get really crazy really quickly. So what I have here is some random objects. I have, for example, the pig, I have a torus, and then they are being grafted with the graph stages node into one scene. So if you select that guy and expand, my main scene is the complete final scene I'm trying to export. For example, this can be a city you're doing for a game or for a movie. So main scene will be your whole city. And for example, pig and torus, they are like elements like the houses, bridges, and whatnot. So it will get really complex as you're developing. And I'm adding some random elements. Maybe you need to add a cube in there. So by this point, I have that. And then I have materials. This is being assigned to the pig head, for example. The materials will also have a path. And we have some variants and lots of complexity. And these networks can get, again, really, really crazy. But you will see that you have lots of parameters. And they all, if I select the end one, they all have to be in the main scene, in the whole city or the whole game level you're doing. If it's not there, the hierarchy is broken and it's not going to work. For example, if I send this instead of being there in the main scene, just in materials, now that guy is outside my main scene and it won't get exported at the end. Right? Really important about hierarchies. So the main scene, the name main scene you see here, which is coming from here, the main city or whatever it is, but this is the main stage, will be in a lot of places, pretty much everywhere. When you're assigning materials, you see it again, main scene, because you're sending it into the proper path. I'm setting some variants, and then you have to send it to the proper path. Then again, main scene, main scene. Now just imagine you're adding more and more, and like a whole forest and characters. Everything has to be in the proper hierarchy. But what happens if, for example, we get a new direction that this is not called main scene anymore, or is another location or something like that? You will have to find in potentially thousands of nodes and nested nodes every time you're calling in that path and change it to the new name. So the exercise for this tool will be to do that automatically and change for all the paths so we can update that name for the main level or the main city or the main stage we're on. So we can freely update to whatever name we want, from old name to a new name. The way we're gonna tackle this is with the same logic we did before, but with a code oriented more for production. We're not gonna select all the root nodes, like this, like this, like this, because it can be thousands of them. But one thing, especially useful with USD networks, at the end they will all conform into one, which will be your exporter. So if we see it that way, we're basically gonna reverse our mind and think, okay, this time this guy is the root node. So we are reversing the tree, and now we only have one root node and we can traverse upwards. And our plan is to go node by node, checking if the old name is in the parameters. But we will add that new efficiency that we will check if you already visited that node or not. So the logic will be similar to the previous tool. We are selecting the input. If I select this node, you have two inputs for this node. You have this one here and this one here. So I already visited this input if I'm following that change from this one. But if you see this node here is also the input for this node. Meaning if I just keep doing the algorithm, will be the same case as before. I will visit this node twice. But we'll do a check now that's gonna skip that if I already visited that node, which will be way more efficient. So let's start doing the tool. I'm here in my Python file. Let's start with the usual import who. We're gonna define a class called USD traversal. Can be many utilities for traversing in stage. As usual, we define a constructor where we're gonna pass just the root. And we're gonna start it with none. Really simple. This root will be the root node we're traversing through the tree. In this case, will be the last node because we are reversing the tree. So let's create just a function to test if all of this is working. Let's call this test. Attach it to the class. Let's just print this is working, just for testing purposes. So if I save this, let's try to call this one from Houdini. Before we had it like this. It's just reloading the module at this point. But now we can access this module, which is the Python file itself, and we can access the classes or functions inside that file. So let's access this class. Let's establish our root node. We're gonna select it again, so it will be who that selected node. This will return a list, so we need to grab the first element. Even if it's just one selection, we have to do it like this. And then the graph is gonna be an instance of that class. So it will be USD traversal, this one here, the one we are reloading. If you type that, now you can access the class on this file, which is also called USD traversal. You need to call in and instantiate the class. And now we can test the methods inside the class. So we can test. If we do graph.test, if everything is correct, we should be seeing this printing statement here. Yeah, this is a mistake because we're not selecting any node. So let's select the root node. We do some space here. We can improve those error messages and say you need to select a node or you need to specify the root node. And this is working. So let's recap that structure one more time. In the Houdini configuration files, I'm creating a scripts folder. Houdini will know about this, but you need to specify this is a Python modules container. You have a folder. In this case, for me, it's called USD utils. Let's take a look at the code again. So I'm calling that one, and I can call it because it has a constructor. Inside, I have this PyCache will be created automatically. Don't worry about that. Inside, I have another constructor, and I have my Python file. So I can call USD utils, and I can call in whatever file I have inside. So inside USD utils, I have USD traversal, which is this one here. And in USD traversal, I'm defining all the classes or functions I need for this project. So now I can reload that. I can establish a root node because I need that for the traversal, and I can start calling the methods for that class. So if I instantiate one of those classes like this, USD traversal in this typing is the name of the class. And now you can call the methods in there. Okay, let's keep going. Quick overview. We are traversing through the nodes. We are checking every parameter. If the name of the parameter contains the string path, we're going to evaluate the string value in the parameter. We're going to check if we have the name, the old name, and we're going to change it to the new name. And the traversal is the reverse version of this tree. We're starting at the bottom. This is our root node going all the way to the top. Let's implement that logic. It's going to be a breadth-first search traversal. But first, let's define a global function, a global method, because this is inside the class. Let's call it setNewPath. We're going to pass in a root node. At the beginning, when we instantiate this class, root is none, but in here, root will become the node we are selecting as root. So we need to say self that root is equals to that root we're passing. We're going to create a visited set equal to an empty set, because this is how we're going to keep track on the nodes we already traveled to. And we need some variables. So the old name is the name we're trying to graph. For right now, let's hardcode to the names we have in the scene. It's called main scene. And let's give it a new name. Let's call it new stage. This will be obviously the new direction we have. If the city was CDA and now maybe CDB or North City or stuff like that. For now, let's just keep it hard-coded like this. And we will need some sort of helper function. Let's call this BFS for breadth-first search, change path. Usually, helper functions will start with an underscore. In production, that means when you instantiate this class, the user using this class will have access to the methods the same way we just tested with the test function is printing this is working. But sometimes you don't necessarily want users to have access to some helper functions. The main reason for these functions is because they're going to be called in another function, like the case here. So in this new function, we will pass in the root, the node we are traversing currently, the set, so the visited set. We're going to pass in the old name and the new name as well. So those are the parameters or arguments for that function. So let's define that helper function. BFS, attach it to the class, and we're passing in the same arguments. So that's visited node, the old name, and the new name. So in this function, we're going to do the same structure we've been doing so far, the breadth first search traversal. So let's establish a queue. It's going to have root, the same node we are currently iterating through, and the same conditions, while the length of that queue is greater than 0, meaning if the queue is not empty, we're going to take a reference to the current node, call this current, and we're going to pop it. Pop, remember how to pop from a queue, has to be the first element. We can print this, the node here as we're traversing, but since we're using the visited set, we're going to do it differently. So let's start this by doing if the current node is in our set, we're not going to do anything because we already saw that node. Let's keep it like that for a second. And then we're going to add to that set, we're going to do with the add function, we're going to add the current node. This will take care of checking if you already traveled to that node or not. And then we need to loop for the children of the current node. So for node in current, that this time we're doing inputs because we are reversing the tree. In the graph we did before, we did it in outputs. This time is the reverse. We're traveling from the bottom, that's our new root node, to the top. So once we are here, you're gonna just append it to the queue, each children. And that's pretty much our traversal. Now let's do the logic to find those parameters. And we're gonna create another function. It will be a helper function at the end too. So let's call this one set params. We can attach it to the class. We need here the node we are currently iterating through. I can keep consistency in calling it root, but it's a node indeed. We need the old name. We need the new name. Now we need to traverse through all the parameters in the current node. So for param in node.params, this Houdini method will give you access to a list of all the parameters in the node. And now we do the check. If the string path is present in the parameter name, then we can grab a reference to that old path because it will be old by this point. Let's call this old path is equal to param.eval as string. Why am I evaluating this as a string? Let's take a look at this. Not all the parameters are of type string. This is a dropdown. It can be numeric values like this one here. And it will give you an error because you're evaluating an integer and you're trying to compare that with a string, the string path. So in order to avoid that error, we can evaluate every node as a string. So if this is a numeric value or like a toggle, for example, these ones, it will switch to on and off. Because it could be the case that one of these toggles is also called path in the name of the parameter. So we need to take account for that. That's why we're evaluating as a string. So we have that. We can print here also the string we are evaluating if you want to do some debugging. For example, print the old path. I'll just keep it like that. If something is wrong, I know the points I can start checking things. Now we can do the condition if old name, which will be in our case main scene, it's present in that old path. I'm doing this because also it could be a case that the parameter is called path, like this one. It has path in there, but you don't have the old name we're trying to find. This is just materials, for example. So we're trying to select all those edge cases. In that case, the new path we're gonna have is equal to the old path, and we're gonna replace the old name with the new name. It's really, really simple. Now we have that new string, and then we can do the set. Param.set the new path. So where we're gonna call this function is actually here. For every time we have a reference to the current node. So we can do an else statement, and only if we haven't visited this node, we're gonna call in that function. So self that set param or set parameters. We pass in the current node, old name, and the new name. And that's the main logic, but there's something wrong in here in terms of how are we grabbing the value of those parameters. If we're evaluating this as a string with this method eval as string, there are some edge cases, especially in the case, for example, of this graph stages node. You actually don't want to change this path, otherwise the structure is going to be messed up. And you will see this expression here, and sometimes you're not visually seeing, for example, the old name, which is main scene. But if I middle click this and I evaluate this, now it's going to reveal that is indeed that name, and you don't want to change this. In Python, we are basically doing that. We are evaluating the string. So we need to take into account these edge cases as well, where, for example, let's check the name of this. The name of this parameter is destPath for destination path. So every time we see that name, we basically don't want to touch it. And we can add that condition in here as well. So if path is present in the name, but we also need to say and the param.name, this will be a method, is not equal to this path. Only then change it. So let's check if this is working. I also added here a string wrapping the old path, because when you evaluate this, it can be also empty and can be some weird numeric values. In order for it to work, it's just safer to have it like this. So let's save that and go back here. I don't think we're printing anything. Let's check how we are importing. The tool is calling in, is instantiating that class, and is calling the method we want. That looks okay. And all the structure is called main scene everywhere. So now let's change that to the new name. Let's run this. And now we officially changed in every single path, and the structure is intact. So now our new main scene, it has a new name called new stage. And if you double check everywhere, even in the variants, the name is updated to new stage. Before was main scene, materials, everywhere basically is changed to the new name. Here as well, in every path. And if you find more edge cases like the graph one, you can keep adding that into your conditions. So that's how the tool works and how the efficiency works as we travel, keep track of the visited nodes, and update the parameters.